What is Dirac equation? Well, any fundamental concepts in physics or mathematics is very well defined when you go through the definition of that particular concept. Right on your screen, as you can see, this is a very simple but a very profound definition of what is the Dirac equation. Now, it has been developed by Paul Dirac, the English mathematician and theoretical physicist, around 1928, and most importantly, go through those which are written and read. Well, it is a relativistic wave equation. In its free form, it includes electromagnetic interactions, and it describes something which is called spin-half particles, and it also says that it is consistent with quantum mechanics and theory of special relativity, and most importantly, it was validated rigorously for the fine structure of the hydrogen spectrum in a completely rigorous way, and it becomes a vital part in building what is called the standard model of particle physics. Now, from this definition, which is simple but yet very profound, certain factors evolved. So the definition actually means what? That definitely it is a relativistic wave equation. Second is that it describes spin-half and massive particles. In its free form, it actually includes electromagnetic interactions. It has been validated by what is called the fine structure of the hydrogen spectrum, and most importantly, it reconciles two big pillars of physics. One is Special Theory of Relativity of Einstein and quantum physics. Well, definitely we are going to explore a little bit more about the English literature or the English definition into a more mathematical way. But the question is that how does the Dirac equation looks? What are the different symbols and how does it look like? Well, if you go with the original form of Dirac equation, it looks something like this. And as you understand, for simplification, theorist and mathematician and physicist works towards it, and it evolved into this or this or this. Now, the last one, which is called the Feynman slash notation, it is not really being used in a very common manner, but the earlier two equations, rather I would say the second part is very commonly used. So as I have told in the earlier equation that it actually shows that it is a relativistic wave equation. It brings together the spin-half particles of electrons. It unites special relativity and quantum mechanics. Most importantly, it actually predicts what is called an antimatter and describes fermions and quantum electrodynamics, and it explains the fine structure of hydrogen spectrum. Well, this is overall what we can say the Dirac equation is. But let us look a little bit more into what are the components of the Dirac equation and what do they actually mean. Because until we understand them, it will be very difficult for us to understand the internal mathematical beauty of Dirac equation. Now, as you can see, I will take component by component, and the first one is the I. Well, it is very common for those who know quantum mechanics. I is the imaginary unit, and I is represented, to use these complex numbers, I square equals to -1. So it, in the presence of this imaginary unit I, ensures that the Dirac equation remain consistent with the principles of quantum mechanics, where wave functions can be complex. The second thing which comes across is this one. Well, this is a very common thing which we have used. It is called the reduced Planck's constant, and it involves terms involving momentum and energy. The third thing which comes across is this one. Well, this will require a little bit more, I would say, explanation, and this is called the gamma matrices, and they satisfy what is called Clifford algebra, and there's a special term which is called the anti-commutation relation, which I will talk to you later. Now, the key points about gamma matrices are that they operate on the four-component spinor, which we will look into that. It is relativistically invariant. That means that it is covariant under Lorentz transformation, and it means that it has the same form in all inertial reference frames. And the anti-commutation relation, which I just talked, it actually follows from the gamma matrices. So I can say the gamma matrices, which require a little bit more elucidation in terms of mathematical terms, actually are essential for describing the relativistic and spinor properties of the electron, and they provide a mathematical framework for understanding the behavior of electrons. Let us move ahead. The next term, which is called this one, well, this is something which is called the partial derivative, and this actually relates to what is called the differentiation of the space-time coordinates, because remember, we are uniting special theory of relativity where time and space are united into a space-time continuum. So if you're uniting special relativity with quantum mechanics, then definitely the space-time coordinates has to work, and it should inherit what is called the contravariant property of special relativity. Well, if you look at other videos, I have actually talked that how later this was replaced by the covariant derivative, etc. I will talk to that later. The next term, which is very common, is called the mass, the m term. But remember that in Dirac equation, it is the rest mass of the fermion, for example electron. So the term is responsible for introducing the mass of the particle into the equation, and ensures that the Dirac equation reduces to the correct non-relativistic, I would say, Schrödinger equation in the low energy regime. The next term, which is very common, you all know, is speed of light. It has to be there because it deals with special relativity where things are moving close or equal to the speed of light. And then comes the most important part, the wave function or the spinor. So it is a 4-component spinor and represents the state of the particle, including both its spin and quantum behavior, because this is something unique to Dirac equation, which none other equation like Klein-Gordon etc. included, is the spin part. And each component of this psi component to different degrees of freedom of the particles, such as spin up, spin down, etc., which we will look later. And what does this zero means? So it actually means that the solutions to the equation corresponds to possible states of the fermion, including energy, momentum, and spin. So that actually covers in overall what is called that the components of the Dirac equation. Now from these components, what actually emerges is something furthermore important. Now if we take the Dirac equation, there are certain important concepts which comes up, and then the rest part of the video we are going to explore that. The first is that it tells about the relativistic generalization of quantum mechanics. That means it extends the Schrödinger equation to account to relativistic effects, ensuring that particles move close to the speed of light. The description of spin half particles means fermions. So these have got half integer spin like electrons, and successfully incorporates intrinsic spin into the quantum framework. As you know, it incorporates special relativity, so it means that the equation is Lorentz invariant, meaning it holds true to all reference frames under special relativity. The wave equations for particles and antiparticles, it predicts the existence of antiparticles, introducing the concept that every particle has a corresponding antiparticle. It has got a spinor solution. That means it is a mathematical object with multiple components, including, we will see that typically the 4 accounting the particle spin. Well, it also unifies quantum mechanics with EM, that means electromagnetism, and the gamma matrices and spinor solution actually provides a natural description of the interaction between fermions and electromagnetic fields. Now this also forms the foundation of quantum field theory, because it serves for describing fermions in quantum field theory, which governs the fermions fields, which interact with other fields. And we will see in detail that Dirac equation explains the fine structure of hydrogen, including the relativistic corrections of the energy levels. Further, it explains what is called the electron's magnetic moment. That means it provides a natural framework for understanding the phenomena like spin orbit coupling and what is called the Zeeman splitting. So these are the essential, these actually emerges from the equation. And from here we are going to take the first, which you see right at the left hand side corner, which is called the relativistic quantum mechanics. So uniting two big pillars of success is the most important part of Dirac equation, and in the next part of the video we are going to look into what is called the relativistic quantum mechanics. Now when we talk of uniting two pillars of physics, it has happened earlier also. Say for example, James Clerk Maxwell, when united electricity and magnetism, this was also a kind of a unison, because electricity and magnetism before Maxwell were thought to be different phenomena, and which he showed in the equation. Rather, the synthesis of the equation shows that electricity and magnetism are basically, are aspects of the same phenomena. Similarly, in case of Dirac equation, we see that special theory of relativity and quantum mechanics are elegantly weaved into this equation, which is called the Dirac equation. Now when we talk of relativistic wave equation, what do we actually mean is that, say for example, we take a kind of a subatomic particles which I have just highlighted in red, and we assume that they move close or maybe equal to the speed of light. So a relativistic wave equation means that we are going to frame an equation where we are going to describe mathematically the behavior of particles which moves close to the speed of light. So wave equation we had, Schrodinger wave equation, etc., but none of them consider things moving close to the speed of light. And whenever we are taking things to the close of speed of light, we are basically depending on Einstein's special theory. So why do we need it? Yes, because we need to describe quantum particles moving close to the speed of light. Now, is there any non-relativistic equation? I was talking that a non-relativistic quantum equation, yes, the Schrodinger equation, which actually express beautifully the rest of the work, except that particles which are not moving close to the speed of light. Now, there is a question that is Dirac equation is the only relativistic wave equation? The answer is a big no, because there is something which is called a Klein-Gordon equation, and we'll take some time out in another video to explain this in detail. But this is another equation which had certain limitations, but this was also a relativistic wave equation which was framed during the time a contemporary earlier to Dirac equation. Now we come to the second part, which I was talking, that it also describes the spin-half particles. Now if you look into the spin-half particles and they are massive, we need to look into the standard model of particle physics. So when we talk of spin-half, we means that particles which obey, which we call the Fermi-Dirac statistics. So we have the bosons, which are called the Bose-Einstein statistics, and then we have the fermions, which obey the Fermi-Dirac statistics. So here you can see this one highlighted and in red and is green are the fermions, and Dirac equation actually talks about the fermions. So the fermions, if we take, actually obeys the Pauli exclusion principle. It has got a spin-half, and it actually distinguishes from bosons which have got a positive integer, and it is the composition of you and me, the entire world, the galaxies, and these are of the composition of ordinary matter as they compose the entire universe. Remember, on the other hand, the bosons, which are the photon, gluon, etc., they behave a little bit different. So the bosons cannot be described in terms of Dirac equation. So what we can say finally is that it explains the behavior of these particles, including how they interact with electromagnetic fields, and naturally for their quantized spin, because we will see that so the Stern-Gerlach experiment, the spin is also quantized, and we need to understand what is called other relativistic effects. So this is all in all what I can tell you about what is called the Dirac equation, the spin-half particles. The most striking feature of the Dirac equation is what is called the Dirac spinor. Now when we talk of a spinor, this is something a little bit different, but before that we will come again and revisit what is called this part, because here you can see the boson are actually the force particles. That means what? That they have got a spin 1, which can be fairly well described by vectors, and which has got spin 0 can be definitely described by scalars. But here comes the wonder boy, which we call the fermions. If you look into the fermions, which are the matter particles, they have got a spin half, and bosons have got a spin 1 or a 0, and this cannot be described by the usual vector, and for that actually what we need is something, an exotic mathematical property, which is called the spinors. Now when we talk of spinor, or specifically Dirac spinor, I will show you an analogy. Now, say for example, we take a vector and we try to rotate the vector around 360 degrees, and we go from here to here to here. And what happens is that when we come back, we actually, return back to the original vector. So it will come back to its original state, the blue one or whatsoever we have started. Now, on the other hand, if I take a spinor, that means, say for example, an electron, which is moving around 360 degrees. So we move around here and then here and then here, and then we try to come back over here. This one, the dark navy blue. So what will happen is that it will come back, but it will have a negative sign. So from here, what we can deduce that spinor is a mathematical object used in physics, especially in quantum physics, to describe particles like electrons that have a spin. Now, as you can see that the vector, which is a familiar object, describe things that move and rotate in space. Spinors are more special. So if you rotate a spinor by 360 degrees, it does not return to its original state. So that is why I gave this negative sign. It actually changes. So the question is that how can we make it come back to its original state? So for that, we need to rotate around 720 degrees. So a full 720 degree rotation will bring back a spinor to its original state where it started. This weird behavior is tied to the quantum mechanical concept of spin, especially for the particles which spin half, the fermions, like the electrons. So that is what actually describes the electron spin. So I hope I can make you understand that this is something. For this we need a different kind of a mathematical object, otherwise things won't happen. So from here what we can see is that a Dirac spinor is so this is the one. So what happens is that a Dirac spinor is basically a kind of I would say mathematical object which combines quantum mechanics with special relativity, and the Dirac spinor has actually 4 components. We will look into that. So here's the definition of what is a spinor. So this is psi has got a 4 component, they are complex valued, and these are the 4 components. Now you see here, these are the 4 components. So the Dirac spinor has got 4 components, and it is used to describe fermions such as electrons in relativistic effect, and the Dirac spinor accounts for both particle and antiparticle. How? For this part of the top, these are representing the spin up and spin down, and they have the positive energy. And this one, which is these both spin up and spin down, they are antiparticle with negative energy, which is crucial in the concept. And remember that when Paul Dirac actually framed the equation, he had no idea about negative energy, and he thought that he has made some errors, some mistakes in the equation. But later, through scientific experiment, it was found that it is not wrong, but this is something which actually exists. The positron, for example. So this is Dirac spinor, which is going to describe something in a 720 degrees coming back to its original state, and it represents both the positive and negative energy. Now what is actually if I take this psi, and if what I am trying to understand the physical interpretation of that, then I can just do according to Born's rule. I can square the amplitude and I can get what is called a probability density, because as we understand, quantum mechanics won't ever give us a particular position or a momentum unlike classical physics. So it would give you the probability density. So now if I take this psi, it reveals something very unique. The first thing is that it tells that spinors transform a specific way under Lorentz transformation. The second is called, remember, Dirac spinor is a bispinor, which states both particles and antiparticles. And the Dirac spinor incorporates spins directly into the structure, and this actually very naturally predicts something which is called the antiparticles, and the Dirac spinor incorporates the effects of special relativity with mass and spin. Now here I have a question for you. We talked that this is, in general quantum mechanics, this psi is used as a wave function. Now what would happen if we could, or Dirac could have replaced the spinor with a wave function? I will look into some of the very interesting observations which I have found through my own research. What is a spinor and a wave function in the next part of the video, and what if this part is replaced as a wave function? This is not a spinor. Let us replace it by a wave function. Here I ask a question: what would happen if Dirac used a wave function instead of a spinor? I mean to say, in physics we also do every kind of a weird experimentation. So let us look into some of the features of a wave function and a spinor, and then only, once we understand the beauty of darkness, we can enjoy the effulgence of light. So here is a kind of an understanding between wave function and spinors. So these are scalar or complex valued functions. These are multiple component. Remember, 2 component like the Weyl equation, spinor, and the 4 component, and so on. Most importantly, it describes the quantum state of particles which has got without spin, because Schrodinger equation during that time, nobody thought that there is something which is called a spin can be incorporated. This has got spin half particles. Now this is a single component, this is called multiple component, which I just showed you. The first 2 parts, the positive energy, the second 2 part, the negative energy of the antiparticle. Now it encodes everything, but it does not include spin, whereas this includes spin, very important. And this transformation simply is under rotation and boosts, and these are under Lorentz transformation, obviously, because it has to take into account the relativistic effects. So this is a kind of a relation, I won't say a difference, but a relation between wave function and spinors. So what if this particular equation is being replaced by a wave function instead of a spinor? I mean to say, it is always better that we can explore these things. So first thing which is going to happen is that we are going to lose spin on information, because a standard wave function, I would say in quantum mechanics, like those with the Schrodinger equation, does not carry any information about the particle spin. So since the Dirac equation is designed to describe fermions, I would say they replace the spinor with a wave function, would remove the spin and the degrees of freedom, and this would create a problem. The second thing which is going to happen is that the Dirac equation predicts the existence of antiparticles through its spinor solutions in particular. So as you can see right on the screen, the 4 components of Dirac spinor represent both the particles and the antiparticle state, along with the different type of spin orientation. Also, there would be no spin orbit coupling, because a wave function alone cannot account for the interaction between the particle spin and its orbital motion, which is known as spin orbit coupling. So spin orbit coupling is a crucial for relativistic effects that contribute to the phenomena like the fine structure of the hydrogen. And most importantly, spinors are essential for correctly describing the behavior of fermions in a relativistic framework. So replacing spinors with wave function could be, like trying to describe bosons, which behave very differently. And finally, there will be a breakdown of Lorentz invariance, because the Dirac equation is formulated to be Lorentz invariant. Under Lorentz transformation, it would break down. So the equation would no longer respect the principles of special relativity, and this won't be considered to be something valid. So that is why wave function is such in Schrodinger equation and spinor is such in Dirac equation. If we replace this, this is going to fail and this is going to happen. Now, as we know, as we have explained earlier when we started this video, that this Dirac equation also explains something which is called the electron's magnetic moment. And that is something very important. We will see that why it is important and what it explains in electron's magnetic moment coming up into the next part of the video. So if we take the classical, I would say, magnetic moment, then it is that means it actually says a measure of how magnetic something is. And it is defined by this mathematical equation where tau is the torque acting on the dipole and B is the magnetic external magnetic field and M is the magnetic moment. I mean, I have mentioned those as bold because of vectors quantities. So you can think of it like a magnet that is with a strong magnetic moment is more likely to align itself with the external magnetic field. The stronger is the magnet, the more forcefully is it aligned. And remember, magnetic moment is a vector quantity. This means it has both magnitude and how strong it is, and direction in which way the magnet is pointing. Now classically, if I take the magnetic moment of an electron, classically the magnetic moment of a particle with a circular spin, I would say it is designed as this. And if we break down the components, this one is basically, which is called the electrons, I would say the charge, MEL, would be the orbital angular momentum, and this would be basically the electron's mass. So remember that the classical approach actually explains the magnetic moment from the electron's orbital motion around the nucleus. But what it does not is that it does not account for the intrinsic spin of the electron, which is a purely quantum mechanical property. So therefore, it could not explain the full magnetic behavior, especially with the fine structure or the anomalous Zeeman effect. So if I take what is called the non-relativistic quantum mechanics, then it actually divides into two parts: the orbital motion and the magnetic field. I mean to say non-relativistic. But if we take relativistic quantum mechanics, then it is something different, because the classical physics does not explain that. It takes basically the orbital motion as something. Now if so Schrodinger equation could not account for the electron's intrinsic spin and its magnetic moment. Now if I take what is called the magnetic moment at spin of the electromagnetic spin of the electron, then it is given by this equation, where this one is basically, which is called is the magnetic moment due to the spin. Now this part is what is called the gyromagnetic ratio, right? And remember, it is basically a dimensionless quantity that relates the magnetic moment of a particle to its angular momentum. So I mean to say, it essentially tells how magnetic a particle is for its given spin. This ME, I would say, is basically the mass of the electron. This E is the electron's charge, and S is the spin angular momentum. Now this spin angular momentum, I'm going to say, for an electron is given by this. Now hold on. What I'm going to do is that I'm going to substitute the angular, I would say, the spin angular momentum into this equation, and this would actually give this kind of an equation. Now why I am doing this will surely become clear in a few seconds from now. So I substituted this. Now what I'm going to do is that for an electron, so if I substitute the approximate value, you can compute the magnetic moment as something like this. And if I take the gyromagnetic ratio, which is roundabout close to 2, you can express this magnetic moment with the what is called the Bohr magneton, and it comes something to this. So what does it mean? That the magnetic moment of the electron due to its spin can also be expressed as this, and this actually means that the magnetic moment due to spin is approximately closely equal to the Bohr magnetron, though it has got a slight correction in terms of quantum electrodynamics. I mean to say, this is something really good, that we can actually calculate, substitute those values, and get an approximately equal to 1 Bohr magneton. Now from here the question comes to the mind is that why classical and pre-Dirac theories were incomplete. As you say, that magnetic moment there was calculated due to its magnetic moment and the orbit, but here we are taking the spin also. So first thing is that what we get in classical physics, there is no notion of intrinsic spin, so that was the limitation. Also before the Dirac equation, intrinsic spin is associated to magnetic moment via the Pauli matrices, which was I want to say not a correct way to do that. Also the Dirac equation was the first to predict naturally the intrinsic spin of the electron, and the equation predicted that the electron has an intrinsic magnetic moment associated with a spin, which is very, I would say, quantized. I mean, the spin won't happen random. It is very quantized. So these are the reasons that it was actually viewed with an internal structure, without any structure. Dirac equation intrinsic spin manually. The Dirac equation was natural to and the equation predicted the electron. So here is a summary that the Dirac equation provided a relativistic framework that actually unified motion, spin, and magnetic moment, and it described, even in the absence, that means even if there is no orbital motion, it gave for a much more accurate prediction for electrons' magnetic moment. This is the counterintuitive part, that how can a particle have an orbital motion without even moving, but in quantum mechanics things become something like that. So we now understand that how it actually explains the electron's magnetic moment, and now we come to what do we mean by massive particles. Now remember, these things are all we are carrying on right from the beginning of the video, one by one. Special relativity, etc., which I showed with arrow. Now when we talk of massive particles, we mean those that do not travel at the speed of light in a vacuum, obviously. For example, electrons, protons, and neutrons are massive because they have a kind of a non-zero rest mass. But massless particles, in contrast, actually travels at the speed of light, which includes, for example, the photons. So all these particles are considered massive. Now, massive doesn't mean a ball or a bottle of bottle of water, etc. In quantum mechanics, when we talk of massive particles, it means really, really small. But those which do not travel at the speed of light and massless are those which travel at the speed of light. So actually what happens is that, for example, if I take the electron's mass, this would be something like this, and this would be mu would be something like this. So when we talk of m not equal to 0, what we try to say is that actually describes a massive particle. So electrons have commonly mass which are given muons, and protons, neutron, they are thought to be composed of composite particles. So what we mean by this is that massive particles where m is not equal to 0, the Dirac equation describes a matter particle. The presence of the mass term leads to the fact that the particle can have energy, and when moving also have a kinetic energy as well. Massless particles, obviously, where m is equal to 0. So now if I talk of m equals to 0, that means massless particles, it would be, but it would be more specifically described in what is called a Weyl equation. Now in this part of the video, I would be talking about how massless particles are described, and this actually leads us to what is known as the Weyl equation. So the Weyl equation, named after the German mathematician Hermann Weyl, is a form of a Dirac equation which also describes fermions, but which has got a mass term equal to 0. So when I make mass m equals to 0, the equation becomes the Weyl equation, which is this, which describes massless particles. Now from here what we can see is that the fourth component, this would be left-handed particles and the right-handed particles. And this is a kind of a Weyl equation where you can see this one actually represents the left-handed and right-handed particles, which has got fermions, and this one is also the same, and this sigma mu are basically called the Pauli matrices, and this actually contains what is called the chirality and helicity, and these things we will cover up later. But what becomes very important from here is that if we do a kind of a comparative study, we understand that massive particles are described by Dirac equation, massless particles are described by Weyl equation. This uses a 4-component Dirac spinor, this is a 2-component Weyl spinor, and includes the mass term. And this has no mass term, as I showed you, the m equals to 0. So left-handed, right-handed states actually do not mix. Right? So that is how these things happen. So the Weyl equation which involves the massless particles. Now we come to what we read in the definition that so Dirac equation is suited for massive particles, and Weyl equation is something which is suited for massless or counterpart. Now from here we come to the final part, which tells that how can you prove actually that Dirac equation is really right? I mean to say, obviously he got the Nobel Prize with Erwin Schrödinger, but basically the thing is that what actually, I mean to say experimentally, how you can validate, or how does it actually proves that. And that is what is called the fine structure of hydrogen. We will look into what is called a fine structure of hydrogen into this part of the video. Now, when we talk of the fine structure of hydrogen, actually, I mean to say, we mean something that the small splitting of the spectral lines in the hydrogen's atom. Now, it is fine, very fine, because it is very subtle. So, in the Bohr model, what is predicted, that can be taken up in more detail. That when an electron in an hydrogen atom transits into different energy levels, it actually produces spectral lines which are very fine. This is a kind of image which you can look into this, and here you can see that the energy levels E1 and E2, they are basically closely spaced, and you can see that the levels E1 and E2 with arrow, that includes the transition. That means the splitting, very fine splitting. Now, if I take a straight line and energy level E, then what I can do is that I can split this. Say, for example, this is actually what is called the splitting. And I can also say that these two lines represent the energy levels after the fine structure, and these dotted lines is during the spin orbit coupling, that how it splits out, right? How it actually splits out. Now, this is a much better picture. So the thing is that what we can see is that the two horizontal lines in the left part represent the fine structure splitting, and the two vertical lines on the right represent the doublet. That means how much actually they're splitting in the emission spectrum. So from here, what we can actually tell is that in case of the earlier Bohr's model, as well as we can say the non-relativistic Schrödinger equation, could explain the basic structure of hydrogen spectral lines, but failed to predict what is called the very fine structure. Why? Because it did not include, number one, the electron spin and the relativistic effects, leading to the inability to account for the small energy, the fine energy levels, which actually splits up, which is called the fine structure of hydrogen. So this is actually what are the limitations. Now, let us look a little bit more mathematically into what we mean by that. So this is a kind of a quantum model, where I am telling that the electron orbits in nucleus in discrete energy levels. I mean to say that typically in case of a Bohr model. And I can say that the electron's energy for when it is moving from one orbit to another, say for example n equals to 1, it would be this, n equals to 2 would be this, and so on. That means very discrete. So the energy levels are determined only by n, which is very discrete. Now, question arises is this. This is the hydrogen absorption and the emission spectrum. The question arises is that the Bohr model ignores the relativistic and the quantum mechanical effects, and it does not reach into account. So what happens when the electron moves close to the speed of light, or I would say when it is approaching significantly close to the speed of light? Let us look into that. So this is the model, and we are saying that electron moves close to the speed of light. We get what is called the Dirac equation. So the electron's energy levels, remember, it is not just the function of the principal quantum number n, but it is also dependent upon the orbital angular momentum and total angular momentum. And that would actually lead to this. The electron's velocity is higher in the lower energy levels. It is coming close to the nucleus, and that would lead to a relativistic correction of the entire form, and this is this equation. And in the next part of the video, I'm going to explain very simply what is this equation, and then you will understand that how the fine structure is being explained and what are the corrections that we need to do, which the Bohr model was unable to do. So on the left hand side, if you see, this is actually the relativistic correction to the energy levels. So it tells actually how much the energy levels shift when relativistic effects are considered, especially representing the fine structure. So in hydrogen like atoms, the total energy of an electron will be the sum of the non-relativistic energy plus the relativistic correction, obviously. Now, if you see the negative sign, it actually indicates that the relativistic correction lowers energy compared to the non-relativistic correction. We will look into this why. And then we come to this Z4. Obviously, this term reflects the fact that the relativistic correction scales strongly with the nuclear charge, Z5 higher, and the correction becomes much larger because the electron moves faster as it is pulled more towards the nucleus. I mean, classically. Then comes this alpha square. This is actually what is called the fine structure constant. It is, I think, around 1 by 137 or 38, and reflects the strength of the electromagnetic interactions. And the correction depends alpha squared because relativistic effects are, I'm sorry because I have written the same thing. Actually, this is the fine structure constant. I'm so sorry for this. This N3 is actually which is called, I would say, the principal quantum number. And why it is N3, we will discuss on that. So factor N3 shows that the relativistic correction gets smaller for the higher energy level. And this entire thing, within the parenthesis, this actually accounts for the quantum number that describes the electron's total angular momentum and the orbital angular momentum, and the correction depends on the electron spin orbit coupling, which mixes the electron spin and the orbital motion. This negative sign, as I told you, is actually lowers the energy compared to the non-relativistic, I would say, prediction. And this is important. This E0 is the non-relativistic energy of the electron of the Bohr model, and this is actually the value which is given by this. So now you see that if we take the typical kind of an energy model, and if I place certain electrons over here, so you understand that the electron's velocity increases and decreases. So this is because the electron moves in a larger orbit. So here it is what is happening. The electron's energy level is increasing, right? Because it is, I would say, nearby to the nucleus. But here it would decrease. So here you see that as the electron moves away from the nucleus, its velocity decreases. And the electron's velocity also decreases as n increases. So n equal to 3, as you understand, that means it has gone to the third orbit. So its energy level is high, but the relativistic correction you will see is less. As it moves closer to the nucleus, its velocity increases. So here is the thing. So this one is actually related upon 1 upon n cube. And since n is in the denominator, larger n values cause the relativistic correction to become smaller. And this is because of the inverse law of the Coulomb. Very simple. So relativistic effects become less significant when the electron is moving slower. That means higher orbit. And it is inverse. As it comes closer, the energy levels are less, but it will be very moving fast because it is near to the nucleus, and there will be more relativistic effects. So as n increases, the electron speed decreases, reducing the relativistic effects. So remember that relativistic effects become less significant when the electron is moving slower. Therefore, as n increases, the electron speed decreases, and the term n3 in the denominator reflects as n increases, the overall magnitude of the relativistic correction becomes smaller. Very simple, because of the Coulomb's law, and this is how things really happen. Now, if I want to say this n3 term, which I just showed you, then the n3 term dependence come from the way quantum mechanical energy levels scale with n and the Coulomb potential. So it comes from the way quantum mechanical energy scales with the Coulomb potential. Larger orbits, that means greater average distance from the nucleus. Lower velocities, since the electron feels the force. Small energy difference between the levels. And from here we can say that relativistic effects are less significant. The same thing, I don't want to repeat. And the term N3 indicates that relativistic correction gets smaller for higher energy levels and for the Coulomb forces at larger distances from the nucleus. So from here we deduce actually 3 things. The one is that the relativistic corrections, which we just saw, Now you saw from the equation what is the relativistic correction and how the energy levels and the relativistic things are taken into account. Second is the spin orbit coupling, the interaction between the spins, electron spin and the angular momentum, and further connections were made by quantum electrodynamics, which is out of the scope of today's video. So from here what we get, all the components. Now if you go back to the first part of the video which I showed with arrow, these things are being covered. So the fine structure is very important because it describes electron spin, the relativistic correction, and the spin orbit coupling. Now you definitely have a question that what is spin orbit coupling and what are those things? And in the next video I am going to cover up these concepts. What is orbital angular momentum, total angular momentum, spin angular momentum, and spin orbit coupling. The concepts and how they describe the relativistic effects coming up into the next part of the video of Dirac equation series. So that's all for today's video. I would be immensely thankful to you for taking up time and watching my videos. If you have liked, please do not forget to subscribe by clicking on the bell icon, and to get all the notification from Physics for Students. You can write to my email ID, which is this, and you can always like and subscribe to my other channel, which is called General Relativity Explained, which contains videos and topics on Einstein's general theory of relativity, and you can follow me on my Facebook, LinkedIn, Instagram and Twitter account. Physics for Students will be soon back with more interesting, mind-boggling, interesting and funny videos, and few more podcasts coming in the month of October. So do not miss, stay tuned, and I will see you in a few days with more interesting and important videos. But till then, goodbye.